All right, practice final, last problem, problem 11, dealing with z transforms. So we're given a transfer function h of z, and we want to find the difference equation describing the system. So let's get started with that. We have part A. We're given h of z, which is the transfer function, right? And the transfer function is going to be equal to the transform of the output, so y of z divided by the transform of the input, which is x of z. And we could then write that y of z is equal to, or excuse me, y of z multiplied by, so I'm just going to multiply that over, and I'll multiply by x of z on both sides, and then I'll have 1 plus 1/2 z to the negative 1 multiplied by 1 minus 1/4 z to the negative 1, and that's all equal to x of z. And if we multiply this out, and then, yeah, I'll write it out. So we'll have y of z, and we multiply it out, we'll have 1, and then we'll have minus 1/4 z to the negative 1 plus 1/2 z to the negative 1. So that'll give us plus 1/4 z to the negative 1. And then we'll have minus 1/8 z to the negative 2. And that's going to equal, if we distribute that y in there, we have y of z plus 1/4 z to the negative 1, y of z minus 1/8 z to the negative 2, y of z, and that is all equal to x of z. Excuse me, x of z. And here's where we can look at our difference, find our difference function. So on table 10, you'll have there's the time shifting property, and say we had some arbitrary signal. We have some signal x of m that has the z transform, big X of z. Well, if we time shift the signal x of n by some time n naught, then the z transform of that is z to the negative n naught times big X of z. And using this relationship right here, we can see that for part A, our difference equation is going to be, what would it be? It would be y of n plus 1/4 y of n minus 1 minus y of n, or excuse me, y minus 1/8 y of n minus 2, and that is equal to x of n. And I'm getting these time shifts right here. These correspond to this exponent right there. Okay. All right. So for part B, before we get to parts B, C, and D, let's get our h of z into something that looks like it's from the table. So we have h of z, and that is equal to 1 plus 1 over 2 z to the negative 1 multiplied by 1 minus 1/4 z to the negative 1, and all this is in the denominator, excuse me. And we want that to look like this. So we'll have a coefficient a, that'll be 1 plus 1/2 z to the negative 1 plus b 1 minus 1/4 z to the negative 1. And you could do this the partial fraction expansion way, or you could do it using what's called the method of residues. And I'll do that rather quickly to expose anybody that hasn't been exposed. So we have, we're working with the coefficient a, so we're going to say a is equal to, and we'll take the limit as z to the negative 1. And what we're trying to do here is we want to say, what does, when we're trying to find a, what do we have to plug in right here for z to the negative 1 to make this whole term, to make 1 plus 1/2 z to the negative 1 equal to 0? And what that would be is 1/2 z to the negative 1 is equal to 1, and then I would multiply, that'd be a -1, and then I would multiply by both sides by 2, so I'd have z to the negative 1 is equal to -2. So I want the limit as z to the negative 1 approaches -2, and I take that term and I multiply it 1 plus 1/2 z to the negative 1 times h of z. And when that happens, so here's my h of z, when that happens, that term gets canceled. So I'll have 1 over 1 minus 1/4, 1 minus 1/4 z to the negative 1. And now I want to evaluate this at z to the negative 1. I no longer have to take the limit because I have nothing, I'm not breaking any mathematical rules, so now I can just write, we're just doing a simple substitution. And that's going to be 1 over 1 minus 1/4 times -2, which is equal to 1 over 1 minus, so we have, what is that? That's plus 1/2, which then that's going to be equal to 1 over 3 over 2, which is equal to 2/3, right? So A is equal to 2 over 3. And for B, it's the same thing. What I would need z to the negative 1 to equal 4, right? Because if z to the negative 1 equals 4, then I'll have -1/4 times 4, which is -1. 1 minus 1 equals 0, and that term goes away. So now I say B is equal to the limit as z of z to the negative 1 as it goes to 4, 1 minus 1/4 z to the negative 1 times h of z. And that leaves me with 1 over 1 plus 1/2 z to the negative 1. I evaluate that at z to the negative 1 equal to 4, and I'll get 1 over 1 plus, I would have 4, what would I have? 1/2 times 4, that's 2. That's a pretty simple one. So I'll get 1/3. So here's my B. So B is equal to 1/3. And that's a very brief and probably not a substantial introduction to method of residues if you haven't seen it before, but there's other YouTube videos out there. So h of z is equal to 2 over 3. All that is divided by, or 2 over 3 is divided by 1 plus 1/2 z to the negative 1 plus 1 over 3, 1 minus 1/4 z to the negative 1. And let's get this up here a little bit. So here's my h of z. All right, so for part B, we want to find the impulse response h of n if it's a two-sided signal. Now, if it's a two-sided signal, that means our regions of convergence have to, well, all regions of convergence have to be the intersection, right? But if it's two-sided, that means that one side of the signal, so if h of z is composed of an h1 of z plus an h2 of z, and it's two-sided, then h1 of z either has to be anti-causal or causal, and then h2 has to be the opposite, right? And if we take a look here, if we said that this one right here is h1 of z, and this one right here is h2 of z, well, if h2 of z is anti-causal, that means its region of convergence is going to be this way, right? And if h1 of z is causal, then its region of convergence is going to be going outward. And we have no intersection, and therefore that we don't have an actual we're not going to be able to take a transform. So in order for us to, in fact, have a two-sided system, that or two-sided signal, then we know that this one's going to have to go inward, and then this one is going to have to go outward. And now our region of convergence is this little torus here, right? So we'll have a causal for part B. For part B, let's write. And we'll just run through all of them real quick. So then for part C, uh, C, it's a right-sided signal. And a right-sided signal that's the same kind of term that we use talking about Laplace transforms, meaning that it's going right half plane, which that's in the S plane, but in the Z plane, a right-sided signal means that it is going from the circle at the location of the pole outward. Okay, so that means here we're going like this, and then at the circle associated with the pole at 1/2, we're going outward as well. And the region of convergence has to be the intersection. So that gives us a region of convergence all out here. So for part C, H1 is causal, H1 and H2. And for part D, if it's a left-sided signal, well, we've kind of used up all but one possible combination, and that means that both of them are going inward, right? They're both going like this. So our region of convergence has to be the intersection, and that's going to be inside of here. So H1 and H2 are anti-causal. And now we can actually get our H of n. So H of n, and this is just using your transform tables. We have a constant coefficient, and if you look at the transform, so when we have that anti-causal signal, we have to include that minus sign, so we'll have minus 2/3, and then we will have minus 1/2 to the n u of minus n minus 1, and then that's going to be plus 1/3, 1/4 to the n u of n, because this, like we said here, H2 is the causal part. So, and then it asks, is the system causal? Let's just take a look. Let's just take a look at H1. Okay, so H1. So let's say we know that H1 of n is equal to minus 2/3, and let's say actually even ignore that coefficient right now. We know it's just, let's just say it's this unit step. Well, what's H1 of -3? Well, we get u of negative 3 minus 1, and we'll get u of 3 minus 1, which is equal to 2. So our input at -3 depends on the future at some time n equals 2. So we know this is not causal. Is it stable? Does it? And for stability, all we have to do is really think about, does this include, does our region of convergence include the unit circle? Well, no, because our region of convergence for part B was this torus here, the donut, right? So it's not stable. And for your justification, you can just write on the exam that the region of convergence does not include the unit circle. Simple enough. All right, now let's do C. Find the impulse response h of n if it's a right-sided signal. We already talked about for part C, H1 and H2 are causal, so H of n is going to equal 2 over 3 minus 1/2 to the n power u of n plus 1 over 3 1 to the 4th to the n u of n. Is it causal? Well, yes, we know it's causal, right? If I want an output at h of, if I put in h of -2, just looking at my unit steps, just isolating that, and then I have u of -2 plus u of -2, right? And I'm not having a look into the future. So that's a causal system. And is it stable? Well, yes, because now we're talking about a region of convergence. We're talking right-sided. It has to be the intersection of them. So we are going this way, outward. And that region of convergence includes my unit circle, so it is stable. All right, for part D, what's the impulse response? If it's a left-sided signal. If it's a left-sided signal, it's in here, right? So we'll have -2 over 3. This one's just repeated from the first part of the problem, so. And we won't have a plus sign, we'll have a minus sign. Minus 1/3, 1 over 4 to the n, u of -n minus 1. And that, again, is just from the table. On the table, on, what is it? It's table 10.2. If we have a signal minus alpha to the n, u of -n minus 1, then that gives us a z transform of 1 over 1 minus alpha z to the -1. And that has a region of convergence, z. The magnitude of z is less than the magnitude of alpha. And if we had, so here's one of them. I probably should have done this at the beginning of the video, I apologize, and if we have a signal alpha n u of n, that gives us a z transform that looks exactly the same. The only difference is that the region of convergence is flipped, meaning that the magnitude of z has to be greater than alpha. And that's where these minus signs come from. There and there and there. The minus sign on the 1/2 is the fact that if we take a look at, where can I get some room here? Yeah, and let's just write 1 over 1 plus 1/2 z to the -1. Well, that's the same as 1 over 1 minus 1/2 z to the -1. So my alpha, to make this look like this down here or this over here, really we're concerned with this or this, then my alpha is equal to -1/2. And that's where those minus signs are popping in and out of. So that's one thing you got to be careful is for this guy right here when you're doing this anti-causal signal. And as far as explaining the causality and the stability, you can just reference the region of convergence. You can say it's not a causal system because it's not right-sided, or you can say it's not a causal system because the region of convergence is a torus or a donut or a strip that closes on itself in the z-plane. You can say it's not stable because it doesn't include the region of, or it doesn't include the unit circle. Or you can, if you wanted to, which is a terrible idea on an exam, but you could write out the summation and prove that it goes that it doesn't converge. So and then it diverges. But just using a z-plane is probably going to be the fastest and clearest way to explain your answer. All right. Good luck on your exam.